Hello everyone, welcome back to the channel. In this video, we are going to be talking about one of the most important topics in solar systems installation, but commonly overlooked. Now, it is nothing but how to properly size breakers for solar systems. Now, before I move any further, I want you to just put in the comment section where you are watching the video from, your location. So I want to know where majority of the viewers are tuning in from. So thank you very much. And now let's get right in. Now, talking about sizing breakers. Breakers are one of the most important protective devices we have or we use during solar systems installations. Not just solar system installations, even electrical installations, mechanical, and what have you. Breakers are very important. They are used for different kinds of setup, different varieties and different margins of setups. Different kinds of breakers perform different functions for different systems. But generally, breakers help to protect your system from fire hazards. Breakers can also help to isolate your system. It serves as a switch or an isolator in case you want to do maintenance. You can easily switch it on and off. Breakers can actually prevent fire outbreak in case of a short circuit. If positive and negative come in contact with each other, then if there's a breaker connected in between, the breaker trips to prevent further damage of the system. With all this, you can see that the importance of using breakers for electrical and every other kinds of systems, or even solar systems, particularly in this class, cannot be overemphasized. Hence, the need for this video, and you need to know how to properly size the breakers, because you cannot just go ahead and use any breaker because you need to use the breaker. There are ways you can size, because these breakers, they have ratings. Now, different ratings are used for different setups. Depending on your setup, that will enable you to determine the size of breaker that you need for that system, for that particular setup. Every solar system installation without these protective breakers would work, but doing that, you would be rest assured that that system is sitting on a time bomb that will explode at any time, and that system is at risk. So to be able to minimize all those risks and to be able to get your system to be running perfectly with minimal risk, you need to put all these things into consideration. This is an example of a breaker. We have AC breakers, we have DC breakers, we have single pole breakers, we have double pole breakers. There are different types, different varieties of breakers, but I'm going to limit them to just single pole and double pole. We'll talk about that later in this class. Then we just try to make sure we make it as elementary as possible. Then in future classes or in future lessons, I'm going to introduce the other types that are also necessary for solar systems installation and protection. For a full solar system setups, we have the panels right here. Then from the panels, you have the controller. I'll use a block diagram. Then from the controller to the batteries, then also from the batteries to the inverter, then from the inverter to the building. This is the complete block diagram of a full solar system setup. Now, these are the panels, then controller, battery, then the inverter, then loads in the house. Breakers are needed at several points within this full network. Now, these various points that are important for you to apply these breakers. Number one, between the panels and the controller, the breaker has to be here. Then also, from the inverter to the battery, a breaker has to be here as well. Then also, lastly, from the inverter to the entire building, a breaker has to be here. And as a feedback to the inverter from the house, or let's say from the grids, we have grid supply to the inverter as input charging. A breaker is expected to be here as well. Now we have four different points where we need to apply or use these breakers. And I'm going to break down each of these parts for you to know how to size the breakers that would fit for each of these parts. Now, first of all, let's get to the panel breakers. You need to understand that the current that flows from the panels to the controller and down to the battery up to these very points is DC. They are all direct currents. I've talked about direct current and alternating currents in my previous class. You can check that out. My first video. Then from here, these two breakers, the current that flows through these breakers are AC. The inverter supplies voltage or current to the house. Then the input from the grid to the inverter is also AC, alternating currents to charge. Now we have AC breakers and we have DC breakers. Of course, between the panels and the controller, we need a DC breaker. The question is how to know the exact rating of breakers to use. It's very key for you to understand that breakers are primarily rated in amperage or amps. Breakers are rated in amperage or amps for short. So when you get a breaker, you want to look at the current rating of that breaker. And that will help you to know what to do in terms of choosing the right breaker for your systems. And I'm going to show you exactly how that is done. Now let's get to it. For the panels on the controller to be able to determine the size of breaker that is needed, there are two parameters you need to understand very carefully. You need to pay close attention to those two parameters. Number one, we have the short circuit current of the panels. ISC is a parameter on nameplate of every panel you buy, every authentic panel you buy. Emphasis on authentic. ISC, short circuit current of each of the panel. Then also, you need to know the configuration of the panel, whether it is parallel or series connection. Now, configuration can either be parallel or series. You see that parallel and series connection comes in each time, all the time, because it's very important. It's a very important topic in solar systems design and installation. If you understand parallel and series connection, 40% of your solar problem is gone. 40%, I can tell you. Because almost everything you do in solar systems, you need to consider these things. Now, I'm going to show you how to do it. For instance, if you have four panels, now you want to connect these panels. If you connect these panels in parallel, what would happen? Note that, let's say the ISC of each panel is around, for a typical 300 watts panels, the ISC is around 9 amps. So let's say 9 amps, 9 amps, 9 amps, 9 amps. Now, the implication of connecting these panels in series, what is series connection? Series connection is connecting like this because it's just plus, minus, plus, minus, plus, minus. And at the end, you have the plus, then you have the minus. Then this is minus, plus, minus, plus, minus, plus, minus. This series connection. The implication of series connection is that when you connect panels in series or anything in series, batteries in series, the voltage will add up according to the number of panels in that particular system. But current will remain the same. Let's assume you're using the same model of panel, the same make. Now, each of these panels, short circuit current is 9 amps. So I'm going to put it down as 9 amps. No matter the amount of panels we connect together, whether we connect 10, 12, 13, 14, 15, 16, only the voltage of each of the panel will add up. But currents would remain the same across the line. Now, we have 9 amps as a short circuit current. We know that we are supposed to connect in series and we know the ISC. So how then do we calculate the size of breakers to use between the panels connected in series, 4 panels connected in series, to this charge controller right here? That's a big question. Now, what do? Just ISC is equal to what? 9 amps. Therefore, breaker size, what's the breaker size now? Breaker size is equal to 9 times, I'm going to multiply by a factor 1.25. Now, this factor was put up by NEC, that's National Electric Code. It's a regulatory body in the United States that recommends standards for safe electrical installations and what have you. Let's multiply by 1.25. So 9 times 1.25 is safety factor, if you like, is 11.25. 11.25 amps is a short circuit current. Now, why is this short circuit current very important? Breakers help to protect against short circuits. That's why we need this short circuit current to be able to size the breaker. So they go hand in hand. We have 11.25 amps. Now you need to understand that in the market, you are not always going to get the exact value that you're looking for, but there are values within that range. Then, if you have 11.25 amps, you can get a 15 amps breaker that would go well with this setup. And that's the size of a breaker for this configuration and for this ISC. 15 amps breaker would do. So at this point, when you connect 4 panels in series, according to that configuration, put a 15 amps DC breaker right here as a DC breaker to do. Okay? How about if you connect them in parallel? You need to understand the implication of connecting solar panels or connecting any system in parallel, the implication in terms of voltage, in terms of current, before you be able to know how to size for that as well. For parallel connection, the reverse is the case. Voltage remains the same, but current adds up. Current adds up. Let's see. Mind you, while you settle that of the current, also notice that when you connect panels in series, the voltage is increasing, the voltage is looking at you. So you need to also understand that these breakers, they have voltage range as well. There's some 15 amps breakers that have lesser voltage, 400 volts, 300 volts or thereabouts. So also check for that as well. But most of the times for small systems, household systems, you don't need to worry about the voltage. All you need to worry about is the current. Once you've settled the current, then you have little or no problems. Now let's go to parallel connection. For parallel connection, you need to understand the implication of connecting panels in parallel. We've dealt with the configuration for series. Now let's talk about parallel. We know the ISC. The ISC remains 9 amps. Okay, so let's draw the parallel connection for 4 panels. So we have this basically 9 amps, 9 amps, 9 amps. Then this is positive, this is negative, positive, negative, positive, negative, and positive, negative. So we have all the positive connected together and all the negative connected together. Something like this. Okay. Then the output here, that's negative. Then all the positive from here, down, 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 positive. That's the output. Now for parallel connection, when you connect panels in parallel, the currents, the total currents, the resultant current is a sum total of the individual current of each panels. So you can say 9 times 4, that's 32 amps. So it is 32 amps. That's the current. Now, this is the total ISC, the total short circuit current for this connection, for this configuration. So it differs. You cannot get a 15 amps breaker and put it here. If you put a 15 amps breaker here, it will melt off within few minutes. Depending on the intensity of the sun, it will melt, or it can even burn instantly. Now, this is the total current, the maximum current that can come out of these panels at the sun peak, at the best producing points of the panel, when the panel at its peak. This is the current. But for short circuit purposes or for fault purposes, when there's a fault, it can go as high as 32 times the factor 1.25. Hence the reason for this factor. So you multiply 32 by 1.25, you have, let's do the multiplication. We have 40. So we have 40 amps. 40 amps. So we have 40 amps after multiplying by this same factor. You see the differences between parallel and series connection. For series connection, you be thinking about getting a small breaker, but for parallel connection, you're thinking about getting bigger breakers or breakers with higher current rating. They are more expensive for sure. These 40 amps after multiplying by the factor of safety. So you can try to build the size of a breaker around this value, 40 amps, but not too far from 40. So we can say around 45 amps. Also consider the sizes of breakers that are available in the market for you to know exactly what to buy. So let's say 45 amps DC breaker. So for series connection, so we have 15 amps. For parallel, we have 45 amps. This parallel and this series. While current is adding up for parallel connection, the voltage for each panel remains the same. So at the output, if this panel is rated 38 VOC, 38, everything here will still be 38 VOC. The voltage does not change at all, but current increases according to the number of panels connected together. So if you have 9 amps, connect 4 panels, that's 9 times 4, 32 amps. So that's what you need to know about sizing breakers for solar panels, between the panels to the controller. You need to understand the configuration, and also you need to assess, you need to check very properly the short circuit current. These are the things, or these are the parameters that will guide you right in making the best choice. Now, another critical point to apply a breaker is between the inverter and the battery. There's a question mark here. This is one of the heaviest current parts for a solar system. The amount of current that flows from this battery to the inverter is what the inverter uses to convert the DC to AC. So there's a very heavy amount of current exchange going on right here. Okay, sometimes the inverter feeds the battery through the charging system in the inverter from the grid. Sometimes the battery supplies the inverter a lot of current exchange. That's corex, not forex. Just joking. Okay, so we have the batteries, then we have the inverter. For instance, we have a 48-volt battery connected to a 5 kVA inverter. Now, this is voltage and this is what? Power. P is equal to IV. So to get the current rating, you are going to do what? Divide the power by the voltage. So we are having 5,000. 5, this K is 1,000, 1,000 volt amps. So 5,000 volt amps divided by 48 volts. So we are having what? 5,000 over 48. 104 amps. 104 amps. So you can consider this the largest amount of current that this battery can supply to the inverter, depending on the load applied to it. If you apply lesser load, it's going to supply lesser current. If you apply more load, it's going to supply more current to the inverter. But for some recent batteries like lithium batteries, you can actually limit the amount of current that the inverter can pull from the battery. Some lithium batteries have discharge or charge current up to 200 amps, even some 250 amps. You can also set the discharge current that you want depending on the loads that you have. So let's go with these 104 amps. 104. Let's just round off to 105. 105 amps. You're also going to multiply by the safety factor of 1.25. So 105 times 1.25 results in what? Let's do the calculation together. 105 times 1.25. 131. 131.25 amps. So it means we are supposed to be getting at close to 130, between 130 to about 150 amps breaker DC thereabouts for the battery side. It's a very big breaker. The current from this battery to the inverter is very large current, potentially a large current. So you need to get a large breaker ready to be used, ready to supply, and ready to also act as a protective device in case of a short circuit. If you connect the battery to the inverter directly without a breaker, what happens when there's a short circuit? If there's a short circuit, mistakenly the positive and negative comes in contact with each other, what happens? There's a very large amount of current, the short circuit current, that goes into the inverter and it will destroy the inverter. So you need to be able to protect the inverter by adding a breaker in between. When you add the breaker, the short circuit current goes through the breaker first. And when the breaker is adequately sized, is properly sized, it's going to trip off or it's going to damage the breaker. It will not get to the inverter. So there'll be an open circuit or a closed circuit on this breaker side. It will prevent the current, that large amount of current due to the short circuit, to go straight to the inverter. So you need to protect these things. These things are not cheap. They are very expensive materials, expensive components. So at every point in time, you need to make sure that your protection systems are intact. Even these protection systems are still not cheap, but it is worth it when you consider the job that it does and when you consider the risk of not using them. You just have to use them anyway. So that is for battery breaker sizing. A lot of systems, a lot of persons install systems that are using battery breaker, but there are some batteries that have inbuilt breakers in them. So you can decide to still add an external breaker if you want to. If you still don't want, no problem. Especially lithium batteries. Lithium batteries, they have built-in breakers. So you might not want to add an external breaker because it does the same job as the breaker inbuilt. Now we are done with the DC. So let's put here 150 amps DC. Batteries can also be connected in parallel and series. But in this case, the connection, the configuration is immaterial because if you know the voltage of the inverter, that will do because the voltage of the inverter is always equal to the voltage of the battery. So that's for that, that settles it. Now let's move over to the AC side. These ones are quite straightforward. Input and output of the inverter in AC. So it depends on the inverter's rated current. For every inverter, there's a rated current both for output and the input. So you need to check the parameters of the inverter to understand what exactly your inverter is capable of. The amount of currents that it can deliver per time. So you need to check that parameter. But some inverters, you will not see the exact current, the exact rated current, but you know the capacity of the inverter as maybe 5 kV or 5 kilowatts. Then you also know the voltage, which is 220 volts AC. That's the output of the inverter. So with this, you can calculate for the current. So all you need to do is to must divide 5,000 by 220 to get the current, the maximum current. So 5,000 by 220, you have 22.7. 22.7. So you're going to size the breaker slightly above 22.7. So let's just say 25 amps. So for your inverter output, before you connect it to the entire house, you need to get this your inverter, this is a breaker, then this is a house. You need this breaker of about 25 amps. There's no safety factor for this calculation, just try to increase it some bit to accommodate for little surges that I want to trip the breaker off. So 25 amps is okay. Also for the input for to the inverter, you also check the input weightings, the input parameters for the inverter. If it's 220 volts or if it's 240 volts, some inverters can accept 230 volts. So you also check the input range and also the input weighting. So let's get a range, let's say from 180 to 220, just let's say 220 volts. 220 volts. Then also divide by the inverter's capacity. The same thing, that's 5,000 over 220 gives you the same thing. So the same thing, 25 amps. There are some inverters that are programmable. You can increase the charging current for the inverter. That's the current with which it charges from the grid. It depends on your settings. If the current you set at this point or on the inverter is 30 amps for grid charging, then you might want to use something a little bit higher. So for this breaker, you might want to use, let's say, about 35 amps or 40 amps thereabouts. So if it's 20 amps, you can set to 20 amps. You don't want the inverter to consume a lot of energy from your meter. So set it to a very lower amperage for charging. So you're going to use the breaker according to the settings for your inverter. There are some inverters that are presets. You cannot change it. Try those old Indian inverters. So also check the input parameters, the current weighting, check the manual for the current weighting. You get it, then you'll be able to know the exact size of breaker to use for that. So that's it for breaker sizing. At this point, if you've not still subscribed to my channel, please just hit the subscribe button, hit the like button, and also share the video in order for the channel to have more visibility. Now, we have different types of breakers. We have smart breakers right now. These smart breakers, you can connect them to a Wi-Fi device and you'll be able to set any of these parameters by yourself on your smartphone. We have double pole breakers, single pole breakers, even triple pole, a lot of them on the market right now. So that's it for this class. And in my next class, I'm going to make sure I talk about how to connect all of these breakers in a protective box. We have this DC breaker, the AC breaker, surge protecting device. Then we have the voltage protector. We have the energy meter, and so on and so forth. Up to about 6 different protective devices on a combiner box. I'm going to talk about that, how to connect it. I'll bring a box live. I'll do the connection so that you see how it is done. So make sure you stay tuned, stay subscribed, and stay well. Wait for the video. I'm going to drop it next. And also, please, if you have any questions, just put them in the comment section and let's rub minds. Let's talk. And let's see in the comment section. So I'll see you again. Thank you very much for listening. I want to say a very big thank you to you for always supporting, for always watching. Till I come your way next time, I remain your one and only electrical beast. See ya.